Spring Framework Overview. Spring makes it easy to create Java enterprise applications. It provides everything you need to embrace the Java language in an enterprise environment, with support for Groovy and Kotlin as alternative languages on the JVM, and with the flexibility to create many kinds of architectures depending on an application's needs. As of Spring Framework 6.0, Spring requires Java 17+. Spring supports a wide range of application scenarios. In a large enterprise, applications often exist for a long time and have to run on a JDK and application server whose upgrade cycle is beyond developer control. Others may run as single jar with the server embedded, possibly in a cloud environment. Yet others may be standalone applications, such as batch or integration workloads, that do not need a server. Spring is open source. It has a large and active community that provides continuous feedback based on a diverse range of real-world use cases. This has helped Spring to successfully evolve over a very long time. What we mean by Spring. The term Spring means different things in different contexts. It can be used to refer to the Spring Framework project itself, which is where it all started. Over time, other Spring projects have been built on top of the Spring Framework. Most often, when people say Spring, they mean the entire family of projects. This reference documentation focuses on the foundation, the Spring Framework itself. The Spring Framework is divided into modules. Applications can choose which modules they need. At the heart are the modules of the core container, including a configuration model and a dependency injection mechanism. Beyond that, the Spring Framework provides foundational support for different application architectures, including messaging, transactional data and persistence, and web. It also includes the Servlet-based Spring MVC web framework and, in parallel, the Spring WebFlux reactive web framework. A note about modules: Spring's framework jars allow for deployment to JDK9's module path, Jigsaw. For use in Jigsaw-enabled applications, the Spring Framework 5 jars come with automatic module name manifest entries which define stable language level module names, spring.core, spring.context, etc., independent from jar artifact names. The jars follow the same naming pattern with, instead of, for example, Spring Core and Spring Context. Of course, Spring's framework jars keep working fine on the class path on both JDK 8 and 9+. History of Spring and the Spring Framework. Spring came into being in 2003 as a response to the complexity of the early J2EE specifications. While some consider Java EE and its modern-day successor Jakarta EE to be in competition with Spring, they are in fact complementary. The Spring programming model does not embrace the Jakarta EE platform specification, rather, it integrates with carefully selected individual specifications from the traditional EE umbrella. 1. Servlet API, JSR 340. 2. WebSocket API, JSR 356. 3. Concurrency Utilities, JSR 236. 4. JSON Binding API, JSR 367. 5. Bin Validation, JSR 303. 6. JPA, JSR 338. 7. JMS, JSR 914. 8. As well as JTA/JCA setups for transaction coordination, if necessary. The Spring Framework also supports the dependency injection, JSR 330, and common annotations, JSR 250, specifications, which application developers may choose to use instead of the Spring-specific mechanisms provided by the Spring Framework. Originally, those were based on common JAVAX packages. As of Spring Framework 6.0, Spring has been upgraded to the Jakarta EE9 level, for example Servlet 5.0+, JPA 3.0+, based on the Jakarta namespace instead of the traditional JAVAX packages. With E9 as the minimum and E10 supported already, Spring is prepared to provide out-of-the-box support for the further evolution of the Jakarta EE APIs. Spring Framework 6.0 is fully compatible with Tomcat 10.1, Jetty 11 and Undertow 2.3 as web servers, and also with Hibernate ORM 6.1. Over time, the role of Java/Jakarta EE in application development has evolved. In the early days of J2E and Spring, applications were created to be deployed to an application server. Today, with the help of Spring Boot, applications are created in a DevOps and cloud-friendly way, with the Servlet container embedded and trivial to change. As of Spring Framework 5, a WebFlux application does not even use the Servlet API directly and can run on servers, such as Netty, that are not Servlet containers. Spring continues to innovate and to evolve. Beyond the Spring Framework, there are other projects, such as Spring Boot, Spring Security, Spring Data, Spring Cloud, Spring Batch, among others. It's important to remember that each project has its own source code repository, issue tracker, and release cadence. See spring.io/projects for the complete list of Spring projects. Design philosophy. When you learn about a framework, it's important to know not only what it does, but what principles it follows. Here are the guiding principles of the Spring Framework. 1. Provide choice at every level. Spring lets you defer design decisions as late as possible. For example, you can switch persistence providers through configuration without changing your code. The same is true for many other infrastructure concerns and integration with third-party APIs. 2. Accommodate diverse perspectives. Spring embraces flexibility and is not opinionated about how things should be done. It supports a wide range of application needs with different perspectives. 3. Maintain strong backward compatibility. Spring's evolution has been carefully managed to force few breaking changes between versions. Spring supports a carefully chosen range of JDK versions and third-party libraries to facilitate maintenance of applications and libraries that depend on Spring. 4. Care about API design. The Spring team puts a lot of thought and time into making APIs that are intuitive and that hold up across many versions and many years. 5. Set high standards for code quality. The Spring Framework puts a strong emphasis on meaningful, current, and accurate JavaDoc. It is one of very few projects that can claim clean code structure with no circular dependencies between packages. Feedback and contributions. For how-to questions or diagnosing or debugging issues, we suggest using Stack Overflow. Click here for a list of the suggested tags to use on Stack Overflow. If you're fairly certain that there is a problem in the Spring Framework or would like to suggest a feature, please use the GitHub issues. If you have a solution in mind or a suggested fix, you can submit a pull request on GitHub. However, please keep in mind that, for all but the most trivial issues, we expect a ticket to be filed in the issue tracker, where discussions take place and leave a record for future reference. For more details, see the guidelines at the Contributing, top-level project page. Getting started. If you are just getting started with Spring, you may want to begin using the Spring Framework by creating a Spring Boot-based application. Spring Boot provides a quick, and opinionated, way to create a production-ready Spring-based application. It is based on the Spring Framework, favors convention over configuration, and is designed to get you up and running as quickly as possible. You can use start.spring.io to generate a basic project or follow one of the Getting Started guides, such as Getting Started Building a RESTful Web Service. As well as being easier to digest, these guides are very task-focused, and most of them are based on Spring Boot. They also cover other projects from the Spring portfolio that you might want to consider when solving a particular problem. Core technologies. This part of the reference documentation covers all the technologies that are absolutely integral to the Spring Framework. Foremost amongst these is the Spring Framework's inversion of control, IOC, container. A thorough treatment of the Spring Framework's IOC container is closely followed by comprehensive coverage of Spring's aspect-oriented programming, AOP, technologies. The Spring Framework has its own AOP framework, which is conceptually easy to understand and which successfully addresses the 80% sweet spot of AOP requirements in Java enterprise programming. Coverage of Spring's integration with Aspect, currently the richest in terms of features and certainly most mature AOP implementation in the Java enterprise space, is also provided. OOP processing can be used to optimize your application ahead of time. It is typically used for native image deployment using GraalVM. The IOC container. This chapter covers Spring's inversion of control, IOC, container. Introduction to the Spring IOC container and beans. This chapter covers the Spring Framework implementation of the inversion of control, IOC, principle. IOC is also known as dependency injection, DI. It is a process whereby objects define their dependencies, that is, the other objects they work with, only through constructor arguments, arguments to a factory method, or properties that are set on the object instance after it is constructed or returned from a factory method. The container then injects those dependencies when it creates the bean. This process is fundamentally the inverse, hence the name, inversion of control, of the bin itself, controlling the instantiation or location of its dependencies by using direct construction of classes or a mechanism such as the service locator pattern. The org.springframework.beans and org.springframework.context packages are the basis for Spring Framework's IOC container. The bin factory interface provides an advanced configuration mechanism capable of managing any type of object. Application context is a sub-interface of bin factory. It adds 1. Easier integration with Spring's AOP features. 2. Message resource handling, for use in internationalization. 3. Event publication. 4. Application layer specific context such as the web application context for use in web applications. In short, the bin factory provides the configuration framework and basic functionality, and the application context adds more enterprise-specific functionality. The application context is a complete superset of the bin factory and is used exclusively in this chapter in descriptions of Spring's IOC container. For more information on using the bin factory instead of the application context, see the section covering the bin factory API. In Spring, the objects that form the backbone of your application and that are managed by the Spring IOC container are called beans. A bin is an object that is instantiated, assembled, and managed by a Spring IOC container. Otherwise, a bin is simply one of many objects in your application. Beans, and the dependencies among them, are reflected in the configuration metadata used by a container. Container overview. The org.springframework.context.application context interface represents the Spring IOC container and is responsible for instantiating, configuring, and assembling the beans. The container gets its instructions on what objects to instantiate, configure, and assemble by reading configuration metadata. The configuration metadata is represented in XML, Java annotations, or Java code. It lets you express the objects that compose your application and the rich interdependencies between those objects. Several implementations of the application context interface are supplied with Spring. In standalone applications, it is common to create an instance of class path XML application context or file system XML application context. While XML has been the traditional format for defining configuration metadata, you can instruct the container to use Java annotations or code as the metadata format by providing a small amount of XML configuration to declaratively enable support for these additional metadata formats. In most application scenarios, explicit user code is not required to instantiate one or more instances of a Spring IOC container. For example, in a web application scenario, a simple 8 or so lines of boilerplate web descriptor XML in the web.xml file of the application typically suffices. See convenient application context instantiation for web applications. If you use the Spring tools for Eclipse, an Eclipse-powered development environment, you can easily create this boilerplate configuration with a few mouse clicks or keystrokes. The following diagram shows a high-level view of how Spring works. Your application classes are combined with configuration metadata so that, after the application context is created and initialized, you have a fully configured and executable system or application. Configuration metadata. As the preceding diagram shows, the Spring IOC container consumes a form of configuration metadata. This configuration metadata represents how you, as an application developer, tell the Spring container to instantiate, configure, and assemble the objects in your application. Configuration metadata is traditionally supplied in a simple and intuitive XML format, which is what most of this chapter uses to convey key concepts and features of the Spring IOC container. XML-based metadata is not the only allowed form of configuration metadata. The Spring IOC container itself is totally decoupled from the format in which this configuration metadata is actually written. These days, many developers choose Java-based configuration for their Spring applications. For information about using other forms of metadata with the Spring container, see 1. Annotation-based configuration. Define beans using annotation-based configuration metadata. 2. Java-based configuration. Define beans external to your application classes by using Java rather than XML files. To use these features, see the at configuration, at bin, at import, and it depends on annotations. Spring configuration consists of at least one and typically more than one bin definition that the container must manage. XML-based configuration metadata configures these beans as bin elements inside a top-level beans element. Java configuration typically uses at-bin annotated methods within a at-configuration class. These bin definitions correspond to the actual objects that make up your application. Typically, you define service layer objects, persistence layer objects such as repositories or data access objects, DAOs, presentation objects such as web controllers, infrastructure objects such as a JPA entity manager factory, JMS queues, and so forth. Typically, one does not configure fine-grained domain objects in the container, because it is usually the responsibility of repositories and business logic to create and load domain objects. The following example shows the basic structure of XML-based configuration metadata. HTTP URL. HTTP URL. Less than, collaborators and configuration for this bin go here, greater than. Less than, collaborators and configuration for this bin go here, greater than. The ID attribute is a string that identifies the individual bin definition. The class attribute defines the type of the bin and uses the fully qualified class name. The value of the ID attribute can be used to refer to collaborating objects. The XML for referring to collaborating objects is not shown in this example. See dependencies for more information. Instantiating a container. The location path or paths supplied to an application context constructor are resource strings that let the container load configuration metadata from a variety of external resources, such as the local file system, the Java class path, and so on. Application context equals new class path XML application context services.xml, deos.xml. After you learn about Spring's IOC container, you may want to know more about Spring's resource abstraction, as described in Resources, which provides a convenient mechanism for reading an input stream from locations defined in a URI syntax. In particular, resource paths are used to construct applications contexts, as described in application contexts and resource paths. The following example shows the service layer objects, services.xml, configuration file. HTTP URL. HTTP URL. org.springframework.samples.jpetstore.services.pet. Store. Service. Impl. Less than. Additional collaborators and configuration for this bin go here, greater than. Less than. More bin definitions for services go here, greater than. The following example shows the data access objects deos.xml file. HTTP URL. HTTP URL. org.springframework.samples.jpetstore.dao.jpa. Account. DAO. Less than. Additional collaborators and configuration for this bin go here, greater than. org.springframework.samples.jpetstore.dao.jpa. Item. DAO. Less than. Additional collaborators and configuration for this bin go here, greater than. Less than. More bin definitions for data access objects go here, greater than. In the preceding example, the service layer consists of the pet store service impl class and two data access objects of the types JPA account DAO and JPA item DAO, based on the JPA object relational mapping standard. The property name element refers to the name of the Java bin property, and the ref element refers to the name of another bin definition. This linkage between ID and ref elements expresses the dependency between collaborating objects. For details of configuring an object's dependencies, see dependencies. Composing XML-based configuration metadata, it can be useful to have bin definitions span multiple XML files. Often, each individual XML configuration file represents a logical layer or module in your architecture. You can use the application context constructor to load bin definitions from all these XML fragments. This constructor takes multiple resource locations, as was shown in the previous section. Alternatively, use one or more occurrences of the import element to load bin definitions from another file or files. The following example shows how to do so. In the preceding example, external bin definitions are loaded from three files: services.xml, messagesource.xml, and themesource.xml. All location paths are relative to the definition file doing the importing, so services.xml must be in the same directory or class path location as the file doing the importing, while messagesource.xml and themesource.xml must be in a resources location below the location of the importing file. As you can see, a leading slash is ignored. However, even that these paths are relative, it is better form not to use the slash at all. The contents of the files being imported, including the top-level beans element, must be valid XML bin definitions, according to the Spring schema. It is possible, but not recommended, to reference files in parent directories using a relative path. Doing so creates a dependency on a file that is outside the current application. In particular, this reference is not recommended for class path URLs, for example, classpath://services.xml, where the runtime resolution process chooses the nearest classpath route and then looks into its parent directory. Classpath configuration changes may lead to the choice of a different, incorrect directory. You can always use fully qualified resource locations instead of relative paths, for example, file c:/config/services.xml or classpath:/config/services.xml. However, be aware that you are coupling your application's configuration to specific absolute locations. It is generally preferable to keep an indirection for such absolute locations, for example, through $, placeholders that are resolved against JVM system properties at runtime. The namespace itself provides the import directive feature. Further configuration features beyond plain bin definitions are available in a selection of XML namespaces provided by Spring, for example, the context and util namespaces. The Groovy bin definition DSL. As a further example for externalized configuration metadata, bin definitions can also be expressed in Spring's Groovy bin definition DSL, as known from the Grails framework. Typically, such configuration live in a Groovy file with the structure shown in the following example. Beans, data source, basic data source, driver class name equals org.hsqldb.jdbc, driver URL equals jdbc hsqldb memgrails, username equals sa, password equals settings equals menu setting. Session factory data source equals data source. My service nested bin equals another bin greater than data source equals data source. This configuration style is largely equivalent to XML bin definitions and even supports Spring's XML configuration namespaces. It also allows for importing XML bin definition files through an import beans directive. Using the container, the application context is the interface for an advanced factory capable of maintaining a registry of different beans and their dependencies. By using the method tGetBin string name, class less than t required type, you can retrieve instances of your beans. The application context lets you read bin definitions and access them, as the following example shows. // create and configure beans. Application context equals new class path XML application context services.xml, deos.xml. // retrieve configured instance. Pet store service equals context.getBin pet store, pet, store, service.class. // use configured instance. List string user list equals service.get, username, list. With Groovy configuration, bootstrapping looks very similar. It has a different context implementation class which is Groovy aware, but also understands XML bin definitions. The following example shows Groovy configuration. Application context equals new generic Groovy application context services.groovy, deos.groovy. The most flexible variant is generic application context in combination with reader delegates, for example, with XML bin definition reader for XML files, as the following example shows. Generic application context equals new generic application context, new XML bin definition reader context. Load bin definition services.xml, deos.xml, context.refresh. You can also use the Groovy bin definition reader for Groovy files, as the following example shows. Generic application context equals new generic application context, new Groovy bin definition reader context. Load bin definition services.groovy, deos.groovy, context.refresh. You can mix and match such reader delegates on the same application context, reading bin definitions from diverse configuration sources. You can then use getBin to retrieve instances of your beans. The application context interface has a few other methods for retrieving beans, but, ideally, your application code should never use them. Indeed, your application code should have no calls to the getBin method at all and thus have no dependency on Spring APIs at all. For example, Spring's integration with web frameworks provides dependency injection for various web framework components such as controllers and JSF-managed beans, letting you declare a dependency on a specific bin through metadata, such as an auto-wiring annotation. Bin overview. A Spring IOC container manages one or more beans. These beans are created with the configuration metadata that you supply to the container, for example, in the form of XML bin definitions. Within the container itself, these bin definitions are represented as bin definition objects, which contain, among other information, the following metadata. 1. A package qualified class name, typically, the actual implementation class of the bin being defined. 2. Bin behavioral configuration elements, which state how the bin should behave in the container, scope, lifecycle callbacks, and so forth. 3. References to other beans that are needed for the bin to do its work. These references are also called collaborators or dependencies. 4. Other configuration settings to set in the newly created object, for example, the size limit of the pool or the number of connections to use in a bin that manages a connection pool. This metadata translates to a set of properties that make up each bin definition. The following table describes these properties. In addition to bin definitions that contain information on how to create a specific bin, the application context implementations also permit the registration of existing objects that are created outside the container by users. This is done by accessing the application context's bin factory through the getBinFactory method, which returns the default listable bin factory implementation. Default listable bin factory supports this registration through the register singleton and register bin definition methods. However, typical applications work solely with beans defined through regular bin definition metadata. Bin metadata and manually supplied singleton instances need to be registered as early as possible, in order for the container to properly reason about them during auto-wiring and other introspection steps. While overriding existing metadata and existing singleton instances is supported to some degree, the registration of new beans at runtime, concurrently with live access to the factory, is not officially supported and may lead to concurrent access exceptions, inconsistent state in the bin container, or both. Naming beans. Every bin has one or more identifiers. These identifiers must be unique within the container that hosts the bean. A bin usually has only one identifier. However, if it requires more than one, the extra ones can be considered aliases. In XML-based configuration metadata, you use the ID attribute, the name attribute, or both to specify bin identifiers. The ID attribute lets you specify exactly one ID. Conventionally, these names are alphanumeric, my bin, some service, etc., but they can contain special characters as well. If you want to introduce other aliases for the bean, you can also specify them in the name attribute, separated by a comma, semicolon, or white space. Although the ID attribute is defined as an XSD string type, bin ID uniqueness is enforced by the container, though not by XML parsers. You are not required to supply a name or an ID for a bin. If you do not supply a name or ID explicitly, the container generates a unique name for that bin. However, if you want to refer to that bin by name, through the use of the ref element or a service locator style lookup, you must provide a name. Motivations for not supplying a name are related to using inner beans and auto-wiring collaborators. The convention is to use the standard Java convention for instance field names when naming beans. That is, bin names start with a lowercase letter and are camel-cased from there. Examples of such names include account manager, account service, user DAO, login controller, and so forth. Naming beans consistently makes your configuration easier to read and understand. Also, if you use Spring AOP, it helps a lot when applying advice to a set of beans related by name. With component scanning in the class path, Spring generates bin names for unnamed components, following the rules described earlier, essentially, taking the simple class name and turning its initial character to lowercase. However, in the unusual, special case when there is more than one character and both the first and second characters are uppercase, the original casing gets preserved. These are the same rules as defined by java.beans.introspector.decapitalize, which Spring uses here. Aliasing a bin outside the bin definition. In a bin definition itself, you can supply more than one name for the bean, by using a combination of up to one name specified by the ID attribute and any number of other names in the name attribute. These names can be equivalent aliases to the same bin and are useful for some situations, such as letting each component in an application refer to a common dependency by using a bin name that is specific to that component itself. Specifying all aliases where the bin is actually defined is not always adequate, however. It is sometimes desirable to introduce an alias for a bin that is defined elsewhere. This is commonly the case in large systems where configuration is split amongst each subsystem, with each subsystem having its own set of object definitions. In XML-based configuration metadata, you can use the alias element to accomplish this. The following example shows how to do so. In this case, a bin, in the same container, named from name may also, after the use of this alias definition, be referred to as toName. For example, the configuration metadata for subsystem A may refer to a data source by the name of subsystem A data source. The configuration metadata for subsystem B may refer to a data source by the name of subsystem data source. When composing the main application that uses both these subsystems, the main application refers to the data source by the name of my data source. To have all three names refer to the same object, you can add the following alias definitions to the configuration metadata. Now each component and the main application can refer to the data source through a name that is unique and guaranteed not to clash with any other definition, effectively creating a namespace, yet they refer to the same bin. If you use Java configuration, the @bin annotation can be used to provide aliases. See using the @bin annotation for details. Instantiating beans. A bin definition is essentially a recipe for creating one or more objects. The container looks at the recipe for a named bin when asked and uses the configuration metadata encapsulated by that bin definition to create, or acquire, an actual object. If you use XML-based configuration metadata, you specify the type, or class, of object that is to be instantiated in the class attribute of the bin element. This class attribute, which, internally, is a class property on a bin definition instance, is usually mandatory. For exceptions, see instantiation by using an instance factory method and bin definition inheritance. You can use the class property in one of two ways. 1. Typically, to specify the bin class to be constructed in the case where the container itself directly creates the bin by calling its constructor reflectively, somewhat equivalent to Java code with the new operator. 2. To specify the actual class containing the static factory method that is invoked to create the object, in the less common case where the container invokes a static factory method on a class to create the bin. The object type returned from the invocation of the static factory method may be the same class or another class entirely. If you want to configure a bin definition for a nested class, you may use either the binary name or the source name of the nested class. For example, if you have a class called something in the com.example package, and this something class has a static nested class called otherthing, they can be separated by a $, or a dot, so the value of the class attribute in a bin definition would be com.example.something's otherthing or com.example.some.thing.other thing. Instantiation with a constructor. When you create a bin by the constructor approach, all normal classes are usable by and compatible with Spring. That is, the class being developed does not need to implement any specific interfaces or to be coded in a specific fashion. Simply specifying the bin class should suffice. However, depending on what type of IOC you use for that specific bin, you may need a default, empty, constructor. The Spring IOC container can manage virtually any class you want it to manage. It is not limited to managing true Java beans. Most Spring users prefer actual Java beans with only a default, no argument, constructor and appropriate setters and getters modeled after the properties in the container. You can also have more exotic non-bin style classes in your container. If, for example, you need to use a legacy connection pool that absolutely does not adhere to the Java bin specification, Spring can manage it as well. With XML-based configuration metadata you can specify your bin class as follows. For details about the mechanism for supplying arguments to the constructor, if required, and setting object instance properties after the object is constructed, see injecting dependencies. Instantiation with a static factory method. When defining a bin that you create with a static factory method, use the class attribute to specify the class that contains the static factory method and an attribute named factory method to specify the name of the factory method itself. You should be able to call this method, with optional arguments, as described later, and return a live object, which subsequently is treated as if it had been created through a constructor. One use for such a bin definition is to call static factories in legacy code. The following bin definition specifies that the bin will be created by calling a factory method. The definition does not specify the type, class, of the returned object, but rather the class containing the factory method. In this example, the create instance method must be a static method. The following example shows how to specify a factory method. The following example shows a class that would work with the preceding bin definition. Public class client service, private static client service equals new client service, private client service, public static client service create instance, return client service. For details about the mechanism for supplying, optional, arguments to the factory method and setting object instance properties after the object is returned from the factory, see dependencies and configuration in detail. Instantiation by using an instance factory method. Similar to instantiation through a static factory method, instantiation with an instance factory method invokes a non-static method of an existing bin from the container to create a new bin. To use this mechanism, Leave the class attribute empty and, in the factory bin attribute, specify the name of a bin in the current, or parent or ancestor, container that contains the instance method that is to be invoked to create the object. Set the name of the factory method itself with the factory method attribute. The following example shows how to configure such a bin. Less than, the factory bin, which contains a method called createClientServiceInstance, greater than. Less than, inject any dependencies required by this locator bin, greater than. Less than, the bin to be created via the factory bin, greater than. The following example shows the corresponding class. Public class default, service, locator, private static client service equals new client, service, impl. Public client service create client service instance, return client, service. One factory class can also hold more than one factory method, as the following example shows. Less than, inject any dependencies required by this locator bin, greater than. The following example shows the corresponding class. Public class default, service, locator. Private static client service equals new client, service, impl. Private static account service equals new account, service, impl. Public client service create client service instance, return client, service. Public account service create account service instance, return account, service. This approach shows that the factory bin itself can be managed and configured through dependency injection, DI. See dependencies and configuration in detail. In Spring documentation, factory bin refers to a bin that is configured in the Spring container and that creates objects through an instance or static factory method. By contrast, factory bin, notice the capitalization, refers to a Spring-specific factory bin implementation class. Determining a bin's runtime type. The runtime type of a specific bin is non-trivial to determine. A specified class in the bin metadata definition is just an initial class reference, potentially combined with a declared factory method or being a factory bin class, which may lead to a different runtime type of the bin, or not being set at all in case of an instance-level factory method, which is resolved via the specified factory bin name instead. Additionally, AOP proxying may wrap a bin instance with an interface-based proxy with limited exposure of the target bin's actual type, just its implemented interfaces. The recommended way to find out about the actual runtime type of a particular bin is a bin factory.getType call for the specified bin name. This takes all of the above cases into account and returns the type of object that a bin factory.getBin call is going to return for the same bin name. Dependencies. A typical enterprise application does not consist of a single object, or bin in the Spring parlance. Even the simplest application has a few objects that work together to present what the end user sees as a coherent application. This next section explains how you go from defining a number of bin definitions that stand alone to a fully realized application where objects collaborate to achieve a goal. Dependency injection. Dependency injection, DI, is a process whereby objects define their dependencies, that is, the other objects with which they work, only through constructor arguments to a factory method, or properties that are set on the object instance after it is constructed or returned from a factory method. The container then injects those dependencies when it creates the bin. This process is fundamentally the inverse, hence the name, inversion of control, of the bin itself controlling the instantiation or location of its dependencies on its own by using direct construction of classes or the service locator pattern. Code is cleaner with the DI principle, and decoupling is more effective when objects are provided with their dependencies. The object does not look up its dependencies and does not know the location or class of the dependencies. As a result, your classes become easier to test, particularly when the dependencies are on interfaces or abstract base classes, which allow for stub or mock implementations to be used in unit tests. DI exists in two major variants: constructor-based dependency injection and setter-based dependency injection. Constructor-based dependency injection. Constructor-based DI is accomplished by the container invoking a constructor with a number of arguments, each representing a dependency. Calling a static factory method with specific arguments to construct the bin is nearly equivalent, and this discussion treats arguments to a constructor and to a static factory method similarly. The following example shows a class that can only be dependency injected with constructor injection. Public class simple movie lister / the simple movie lister has a dependency on a movie finder. Private final movie finder movie finder / a constructor so that the Spring container can inject a movie finder. Public simple movie lister movie finder movie finder. This movie finder equals movie finder / business logic that actually uses the injected movie finder is omitted. Notice that there is nothing special about this class. It is a POJO that has no dependencies on container-specific interfaces, base classes, or annotations. Constructor argument resolution. Constructor argument resolution matching occurs by using the argument's type. If no potential ambiguity exists in the constructor arguments of a bin definition, the order in which the constructor arguments are defined in a bin definition is the order in which those arguments are supplied to the appropriate constructor when the bin is being instantiated. Consider the following class. Package XY. Public class thing 1. Public thing 1 thing 2 thing 2, thing 3 thing 3, // Assuming that the thing 2 and thing 3 classes are not related by inheritance, no potential ambiguity exists. Thus, the following configuration works fine, and you do not need to specify the constructor argument indexes or types explicitly in the constructor arg element. When another bin is referenced, the type is known, and matching can occur, as was the case with the preceding example. When a simple type is used, such as value true / value Spring cannot determine the type of the value, and so cannot match by type without help. Consider the following class. Package examples. Public class example, bin / number of years to calculate the ultimate answer. Private final int years / the answer to life, the universe, and everything. Private final string ultimate answer. Public example bin int years, string ultimate answer. This years equals years, this ultimate answer equals ultimate answer. In the preceding scenario, the container can use type matching with simple types if you explicitly specify the type of the constructor argument by using the type attribute, as the following example shows. You can use the index attribute to specify explicitly the index of constructor arguments, as the following example shows. In addition to resolving the ambiguity of multiple simple values, specifying an index resolves ambiguity where a constructor has two arguments of the same type. You can also use the constructor parameter name for value disambiguation, as the following example shows. Keep in mind that, to make this work out of the box, your code must be compiled with the debug flag enabled so that Spring can look up the parameter name from the constructor. If you cannot or do not want to compile your code with the debug flag, you can use the @constructor properties JDK annotation to explicitly name your constructor arguments. The sample class would then have to look as follows. Package examples. Public class example, bin / fields omitted, @constructor properties years, ultimate answer, public example bin int years, string ultimate answer. This years equals years, this ultimate answer equals ultimate answer. Setter-based dependency injection. Setter-based DI is accomplished by the container calling setter methods on your beans after invoking a no-argument constructor or a no-argument static factory method to instantiate your bin. The following example shows a class that can only be dependency injected by using pure setter injection. This class is conventional Java. It is a POJO that has no dependencies on container-specific interfaces, base classes, or annotations. Public class simple movie lister / the simple movie lister has a dependency on the movie finder. Private movie finder movie finder / a setter method so that the Spring container can inject a movie finder. Public void set movie finder movie finder movie finder. This movie finder equals movie finder / business logic that actually uses the injected movie finder is omitted. The application context supports constructor-based and setter-based DI for the beans it manages. It also supports setter-based DI after some dependencies have already been injected through the constructor approach. You configure the dependencies in the form of a bin definition, which you use in conjunction with property editor instances to convert properties from one format to another. However, most Spring users do not work with these classes directly, that is, programmatically, but rather with XML bin definitions, annotated components, that is, classes annotated with @component, @controller, and so forth, or bin methods in Java-based @configuration classes. These sources are then converted internally into instances of bin definition and used to load an entire Spring IOC container instance. Since you can mix constructor-based and setter-based DI, it is a good rule of thumb to use constructors for mandatory dependencies and setter methods or configuration methods for optional dependencies. Note that use of the @autowired annotation on a setter method can be used to make the property be a required dependency. However, constructor injection with programmatic validation of arguments is preferable. The Spring team generally advocates constructor injection, as it lets you implement application components as immutable objects and ensures that required dependencies are not null. Furthermore, constructor-injected components are always returned to the client, calling code in a fully initialized state. As a side note, a large number of constructor arguments is a bad code smell, implying that the class likely has too many responsibilities and should be refactored to better address proper separation of concerns. Setter injection should primarily only be used for optional dependencies that can be assigned reasonable default values within the class. Otherwise, not null checks must be performed everywhere the code uses the dependency. One benefit of setter injection is that setter methods make objects of that class amenable to reconfiguration or re-injection later. Management through JMX and beans is therefore a compelling use case for setter injection. Use the DI style that makes the most sense for a particular class. Sometimes, when dealing with third-party classes for which you do not have the source, the choice is made for you. For example, if a third-party class does not expose any setter methods, then constructor injection may be the only available form of DI. Dependency resolution process. The container performs bin dependency resolution as follows. 1. The application context is created and initialized with configuration metadata that describes all the beans. Configuration metadata can be specified by XML, Java code, or annotations. 2. For each bin, its dependencies are expressed in the form of properties, constructor arguments, or arguments to the static factory method, if you use that instead of a normal constructor. These dependencies are provided to the bean when the bin is actually created. 3. Each property or constructor argument is an actual definition of the value to set, or a reference to another bin in the container. 4. Each property or constructor argument that is a value is converted from its specified format to the actual type of that property or constructor argument. By default, Spring can convert a value supplied in string format to all built-in types, such as int, long, string, boolean, and so forth. The Spring container validates the configuration of each bin as the container is created. However, the bin properties themselves are not set until the bin is actually created. Beans that are singleton scoped and set to be pre-instantiated, the default, are created when the container is created. Scopes are defined in bin scopes. Otherwise, the bin is created only when it is requested. Creation of a bin potentially causes a graph of beans to be created, as the bean's dependencies and its dependencies, and so on, are created and assigned. Note that resolution mismatches among those dependencies may show up late, that is, on first creation of the affected bin. If you use predominantly constructor injection, it is possible to create an unresolvable circular dependency scenario. For example, Class A requires an instance of Class B through constructor injection, and Class B requires an instance of Class A through constructor injection. If you configure beans for classes A and B to be injected into each other, the Spring IOC container detects this circular reference at runtime and throws a bin. Currently, in creation exception. One possible solution is to edit the source code of some classes to be configured by setters rather than constructors. Alternatively, avoid constructor injection and use setter injection only. In other words, although it is not recommended, you can configure circular dependencies with setter injection. Unlike the typical case, with no circular dependencies, a circular dependency between bin A and bin B forces one of the beans to be injected into the other prior to being fully initialized itself, a classic chicken and egg scenario. You can generally trust Spring to do the right thing. It detects configuration problems, such as references to non-existent beans and circular dependencies, at container load time. Spring sets properties and resolves dependencies as late as possible, when the bin is actually created. This means that a Spring container that has loaded correctly can later generate an exception when you request an object if there is a problem creating that object or one of its dependencies. For example, the bin throws an exception as a result of a missing or invalid property. This potentially delayed visibility of some configuration issues is why application context implementations by default pre-instantiate singleton beans, at the cost of some upfront time and memory to create these beans before they are actually needed. You discover configuration issues when the application context is created, not later. You can still override this default behavior so that singleton beans initialize lazily, rather than being eagerly pre-instantiated. If no circular dependencies exist, when one or more collaborating beans are being injected into a dependent bin, each collaborating bin is totally configured prior to being injected into the dependent bin. This means that, if bin A has a dependency on bin B, the Spring IOC container completely configures bin B prior to invoking the setter method on bin A. In other words, the bin is instantiated. If it is not a pre-instantiated singleton, its dependencies are set, and the relevant lifecycle methods, such as a configured init method or the initializing bin callback method, are invoked. Examples of dependency injection. The following example uses XML-based configuration metadata for setter-based DI. A small part of a Spring XML configuration file specifies some bin definitions as follows: less than, setter injection using the nested ref element, greater than. Less than, setter injection using the neta ref attribute, greater than. The following example shows the corresponding example bin class. Public class example, bin. Private another bin bin, 1. Private yet another bin bin, 2. Private int I. Public void set bin 1 another bin bin 1. This dot bin 1 equals bin 1. Public void set bin 2 yet another bin bin 2. This dot bin 2 equals bin 2. Public void set integer property int I. This dot I equals I. In the preceding example, setters are declared to match against the properties specified in the XML file. The following example uses constructor-based DI. Less than, constructor injection using the nested ref element, greater than. Less than, constructor injection using the neta ref attribute, greater than. The following example shows the corresponding example bin class. Public class example, bin. Private another bin bin, 1. Private yet another bin bin, 2. Private int I. Public example bin another bin, yet another bin, int I. This dot bin 1 equals another bin, this dot bin 2 equals yet another bin, this dot I equals I. The constructor arguments specified in the bin definition are used as arguments to the constructor of the example bin. Now consider a variant of this example, where, instead of using a constructor, Spring is told to call a static factory method to return an instance of the object. The following example shows the corresponding example bin class. Public class example, bin. // a private constructor. Private example bin. // a static factory method. The arguments to this method can be // considered the dependencies of the bin that is returned, / regardless of how those arguments are actually used. Public static example bin create instance, another bin, yet another bin, int I. Example bin eb equals new example bin, / some other operations. Return eb. Arguments to the static factory method are supplied by constructor arg elements, exactly the same as if a constructor had actually been used. The type of the class being returned by the factory method does not have to be of the same type as the class that contains the static factory method, although, in this example, it is. An instance, non-static, factory method can be used in an essentially identical fashion, aside from the use of the factory bin attribute instead of the class attribute, so we do not discuss those details here. Dependencies and configuration in detail. As mentioned in the previous section, you can define bin properties and constructor arguments as references to other managed beans, collaborators, or as values defined inline. Spring's XML-based configuration metadata supports sub-element types within its property and constructor arg elements for this purpose. Straight values, primitives, strings, and so on. The value attribute of the property element specifies a property or constructor argument as a human-readable string representation. Spring's conversion service is used to convert these values from a string to the actual type of the property or argument. The following example shows various values being set. Less than results in a set driver class name string call, greater than. The following example uses the p namespace for even more succinct XML configuration. HTTP URL. HTTP URL. The preceding XML is more succinct. However, typos are discovered at runtime rather than design time, unless you use an IDE, such as IntelliJ IDEA or the Spring tools for Eclipse, that supports automatic property completion when you create bin definitions. Such IDE assistance is highly recommended. You can also configure a java.util.properties instance, as follows. bin.i.d. equals mappings class equals org.springframework.context.support.property sources placeholder configure a greater than. Less than, typed as a java.util.properties, greater than property name equals properties greater than value jdbc.driver.class name equals com.mysql.jdbc.driver. jdbc.url equals jdbc mysql //localhost 3306 /mid /value /property /bin. The Spring container converts the text inside the value element into a java.util.properties instance by using the Java Beans property editor mechanism. This is a nice shortcut, and is one of a few places where the Spring team do favor the use of the nested value element over the value attribute style. The idref element. The idref element is simply an error-proof way to pass the ID, a string value, not a reference, of another bin in the container to a constructor arg or property element. The following example shows how to use it. The preceding bin definition snippet is exactly equivalent, at runtime, to the following snippet. The first form is preferable to the second, because using the idref tag lets the container validate at deployment time that the referenced, named bin actually exists. In the second variation, no validation is performed on the value that is passed to the target name property of the client bin. Typos are only discovered, with most likely fatal results, when the client bin is actually instantiated. If the client bin is a prototype bean, this typo and the resulting exception may only be discovered long after the container is deployed. The local attribute on the idref element is no longer supported in the 4.0 beans XSD, since it does not provide value over a regular bin reference anymore. Change your existing idref local references to idref bin when upgrading to the 4.0 schema. A commonplace, at least in versions earlier than Spring 2.0, where the idref element brings value is in the configuration of AOP interceptors in a proxy factory bin definition. Using idref elements when you specify the interceptor names prevents you from misspelling an interceptor ID. References to other beans, collaborators. The ref element is the final element inside a constructor arg or property definition element. Here, You set the value of the specified property of a bin to be a reference to another bin, a collaborator, managed by the container. The referenced bin is a dependency of the bin whose property is to be set, and it is initialized on demand as needed before the property is set. If the collaborator is a singleton bin, it may already be initialized by the container. All references are ultimately a reference to another object. Scoping and validation depend on whether you specify the ID or name of the other object through the bin or parent attribute. Specifying the target bin through the bin attribute of the ref tag is the most general form and allows creation of a reference to any bin in the same container or parent container, regardless of whether it is in the same XML file. The value of the bin attribute may be the same as the ID attribute of the target bin or be the same as one of the values in the name attribute of the target bin. The following example shows how to use a ref element. Specifying the target bin through the parent attribute creates a reference to a bin that is in a parent container of the current container. The value of the parent attribute may be the same as either the ID attribute of the target bin or one of the values in the name attribute of the target bin. The target bin must be in a parent container of the current one. You should use this bin reference variant mainly when you have a hierarchy of containers and you want to wrap an existing bin in a parent container with a proxy that has the same name as the parent bin. The following pair of listings shows how to use the parent attribute. Less than, in the child, descendant, context, greater than bin I.d. equals account service less than, bin name is the same as the parent bin, greater than class equals org.springframework.aop.framework.proxy factory bin greater than property name equals target greater than ref parent equals account service, greater than less than. Notice how we refer to the parent bin, greater than / property less than. Insert other configuration and dependencies as required here, greater than / bin. The local attribute on the ref element is no longer supported in the 4.0 beans XSD, since it does not provide value over a regular bin reference anymore. Change your existing ref local references to ref bin when upgrading to the 4.0 schema. Inner beans. A bin element inside the property or constructor arg elements defines an inner bin, as the following example shows. Less than, instead of using a reference to a target bin, simply define the target bin inline, greater than. An inner bin definition does not require a defined ID or name. If specified, the container does not use such a value as an identifier. The container also ignores the scope flag on creation, because inner beans are always anonymous and are always created with the outer bin. It is not possible to access inner beans independently or to inject them into collaborating beans other than into the enclosing bin. As a corner case, it is possible to receive destruction callbacks from a custom scope, for example, for a request-scoped inner bin contained within a singleton bin. The creation of the inner bin instance is tied to its containing bin, but destruction callbacks let it participate in the request scope's lifecycle. This is not a common scenario. Inner beans typically simply share their containing beans scope. Collections. The list set map and props elements set the properties and arguments of the Java collection types list, set, map, and properties, respectively. The following example shows how to use them. Bin.i.d. equals more complex object class equals example.complex object greater than less than, results in a set admin emails java.util.properties call, greater than property name equals admin emails greater than props prop key equals administrator greater than administrator at example.org/prop prop key equals support greater than support at example.org/prop prop key equals development greater than development at example.org/prop/prop/property less than, results in a set some list java.util.list call, greater than property name equals some list greater than list value greater than a list element followed by a reference /value ref bin equals my data source, greater than /list /property less than, results in a set some map java.util.map call, greater than property name equals some map greater than map entry key equals an entry value equals just some string, greater than entry key equals a ref value ref equals my data source, greater than /map /property less than, results in a set some set java.util.set call, greater than property name equals some set greater than set value just some string slash value ref bin equals my data source greater than slash set slash property slash bin. The value of a map key or value, or a set value, can also be any of the following elements: bin, ref, idref, list, set, map, props, value, null. Collection merging. The Spring container also supports merging collections. An application developer can define a parent list map set or props element and have child list map set or props elements inherit and override values from the parent collection. That is, the child collection's values are the result of merging the elements of the parent and child collections, with the child's collection elements overriding values specified in the parent collection. This section on merging discusses the parent-child bin mechanism. Readers unfamiliar with parent and child bin definitions may wish to read the relevant section before continuing. The following example demonstrates collection merging. Bins bin I.d. equals parent abstract equals true class equals example. Complex object greater than property name equals admin emails greater than props prop key equals administrator greater than administrator at example.com/prop prop key equals support greater than support at example.com/prop/prop/property/bin I.d. equals child parent equals parent greater than property name equals admin emails greater than less than. The merge is specified on the child collection definition. Greater than props merge equals true greater than prop key equals sales greater than sales at example.com/prop prop key equals support greater than support at example.co.uk/prop/props/property/bin beans. Notice the use of the merge equals true attribute on the props element of the admin emails property of the child bin definition. When the child bin is resolved and instantiated by the container, the resulting instance has an admin emails properties collection that contains the result of merging the child's admin emails collection with the parent's admin emails collection. The following listing shows the result. Administrator equals administrator at example.com. Sales equals sales at example.com. Support equals support at example.co.uk. The child properties collection's value set inherits all property elements from the parent props and the child's value for the support value overrides the value in the parent collection. This merging behavior applies similarly to the list map and set collection types. In the specific case of the list element, the semantics associated with the list collection type, that is, the notion of an ordered collection of values, is maintained. The parent's values precede all of the child list's values. In the case of the map, set, and properties collection types, no ordering exists. Hence, no ordering semantics are in effect for the collection types that underlie the associated map, set, and properties implementation types that the container uses internally. Limitations of collection merging: you cannot merge different collection types, such as a map and a list. If you do attempt to do so, an appropriate exception is thrown. The merge attribute must be specified on the lower, inherited, child definition. Specifying the merge attribute on a parent collection definition is redundant and does not result in the desired merging. Strongly typed collection. Thanks to Java's support for generic types, you can use strongly typed collections. That is, it is possible to declare a collection type such that it can only contain, for example, string elements. If you use Spring to dependency inject a strongly typed collection into a bin, you can take advantage of Spring's type conversion support such that the elements of your strongly typed collection instances are converted to the appropriate type prior to being added to the collection. The following Java class and bin definition show how to do so. Public class sum, class. Private map string, float accounts. Public void set accounts map string, float accounts. This .accounts equals accounts. When the accounts property of the something bin is prepared for injection, the generics information about the element type of the strongly typed map string, float is available by reflection. Thus, Spring's type conversion infrastructure recognizes the various value elements as being of type float, and the string values, 9.99, 2.75, and 3.99, are converted into an actual float type. Null and empty string values, Spring treats empty arguments for properties and the like as empty strings. The following XML-based configuration metadata snippet sets the email property to the empty string value. The preceding example is equivalent to the following Java code. The null element handles null values. The following listing shows an example. The preceding configuration is equivalent to the following Java code. XML shortcut with the p namespace. The p namespace lets you use the bin elements attributes, instead of nested property elements, to describe your property values collaborating beans, or both. Spring supports extensible configuration formats with namespaces, which are based on an XML schema definition. The beans configuration format discussed in this chapter is defined in an XML schema document. However, the p namespace is not defined in an XSD file and exists only in the core of Spring. The following example shows two XML snippets. The first uses standard XML format and the second uses the p namespace, that resolve to the same result. HTTP URL. HTTP URL. The example shows an attribute in the p namespace called email in the bin definition. This tells Spring to include a property declaration. As previously mentioned, the p namespace does not have a schema definition, so you can set the name of the attribute to the property name. This next example includes two more bin definitions that both have a reference to another bin. HTTP URL. HTTP URL. This example includes not only a property value using the p namespace but also uses a special format to declare property references. Whereas the first bin definition uses property name equals spouse ref equals Jane, greater than to create a reference from bin John to bin Jane, the second bin definition uses p spouse ref equals Jane as an attribute to do the exact same thing. In this case, spouse is the property name, whereas the ref part indicates that this is not a straight value but rather a reference to another bin. The p namespace is not as flexible as the standard XML format. For example, the format for declaring property references clashes with properties that end in ref, whereas the standard XML format does not. We recommend that you choose your approach carefully and communicate this to your team members to avoid producing XML documents that use all three approaches at the same time. XML shortcut with the C namespace. Similar to the XML shortcut with the P namespace, the C namespace, introduced in Spring 3.1, allows inline attributes for configuring the constructor arguments rather than nested constructor arg elements. The following example uses the C namespace to do the same thing as the from constructor-based dependency injection. HTTP URL. HTTP URL, less than, traditional declaration with optional argument names, greater than. Less than, C namespace declaration with argument names, greater than. The C namespace uses the same conventions as the P, 1, a trailing ref for bin references, for setting the constructor arguments by their names. Similarly, it needs to be declared in the XML file even though it is not defined in an XSD schema, it exists inside the Spring core. For the rare cases where the constructor argument names are not available, usually if the bytecode was compiled without debugging information, you can use fallback to the argument indexes, as follows. Due to the XML grammar, the index notation requires the presence of the leading underscore, as XML attribute names cannot start with a number, even though some IDEs allow it. A corresponding index notation is also available for constructor arg elements but not commonly used since the plain order of declaration is usually sufficient there. In practice, the constructor resolution mechanism is quite efficient in matching arguments, so unless you really need to, we recommend using the name notation throughout your configuration. Compound property names. You can use compound or nested property names when you set bin properties, as long as all components of the path except the final property name are not null. Consider the following bin definition. The something bin has a Fred property, which has a Bob property, which has a Sammy property, and that final Sammy property is being set to a value of 123. In order for this to work, the Fred property of something and the Bob property of Fred must not be null after the bin is constructed. Otherwise, a null pointer exception is thrown. Using depends on. If a bin is a dependency of another bin, that usually means that one bin is set as a property of another. Typically you accomplish this with the ref element in XML-based configuration metadata. However, sometimes dependencies between bins are less direct. An example is when a static initializer in a class needs to be triggered, such as for database driver registration. The depends on attribute can explicitly force one or more bins to be initialized before the bin using this element is initialized. The following example uses the depends on attribute to express a dependency on a single bin. To express a dependency on multiple bins, supply a list of bin names as the value of the depends on attribute, commas, whitespace, and semicolons are valid delimiters. The depends on attribute can specify both an initialization time dependency and, in the case of singleton bins only, a corresponding destruction time dependency. Dependent bins that define a depends on relationship with a given bin are destroyed first, prior to the given bin itself being destroyed. Thus, depends on can also control shutdown order. Lazy initialized bins. By default, application context implementations eagerly create and configure all singleton bins as part of the initialization process. Generally, this pre-instantiation is desirable because errors in the configuration or surrounding environment are discovered immediately, as opposed to hours or even days later. When this behavior is not desirable, you can prevent pre-instantiation of a singleton bin by marking the bin definition as being lazy initialized. A lazy initialized bin tells the IOC container to create a bin instance when it is first requested, rather than at startup. In XML, this behavior is controlled by the lazy init attribute on the bin element, as the following example shows. When the preceding configuration is consumed by an application context, the lazy bin is not eagerly pre-instantiated when the application context starts, whereas the not.lazy bin is eagerly pre-instantiated. However, when a lazy initialized bin is a dependency of a singleton bin that is not lazy initialized, the application context creates the lazy initialized bin at startup, because it must satisfy the singleton's dependencies. The lazy initialized bin is injected into a singleton bin elsewhere that is not lazy initialized. You can also control lazy initialization at the container level by using the default lazy init attribute on the bins element, as the following example shows. Auto-wiring collaborators. The Spring container can auto-wire relationships between collaborating bins. You can let Spring resolve collaborators, other bins, automatically for your bin by inspecting the contents of the application context. Auto-wiring has the following advantages. 1. Auto-wiring can significantly reduce the need to specify properties or constructor arguments. Other mechanisms, such as a bin template discussed elsewhere in this chapter, are also valuable in this regard. 2. Auto-wiring can update a configuration as your objects evolve. For example, if you need to add a dependency to a class, that dependency can be satisfied automatically without you needing to modify the configuration. Thus, auto-wiring can be especially useful during development, without negating the option of switching to explicit wiring when the code base becomes more stable. When using XML-based configuration metadata, see dependency injection, you can specify the auto-wire mode for a bin definition with the auto-wire attribute of the bin element. The auto-wiring functionality has 4 modes. You specify auto-wiring per bin and can thus choose which ones to auto-wire. The following table describes the 4 auto-wiring modes. No. Default, no auto-wiring. Bin references must be defined by ref elements. Changing the default setting is not recommended for larger deployments, because specifying collaborators explicitly gives greater control and clarity. To some extent, it documents the structure of a system. By name. Auto-wiring by property name. Spring looks for a bin with the same name as the property that needs to be auto-wired. For example, if a bin definition is set to auto-wire by name and it contains a master property, that is, it has a setMaster method, Spring looks for a bin definition named master and uses it to set the property. By type. Lets a property be auto-wired if exactly one bin of the property type exists in the container. If more than one exists, a fatal exception is thrown, which indicates that you may not use by type auto-wiring for that bin. If there are no matching beans, nothing happens, the property is not set. Constructor. Analogous to by type but applies to constructor arguments. If there is not exactly one bin of the constructor argument type in the container, a fatal error is raised. With by type or constructor auto-wiring mode, you can wire arrays and typed collections. In such cases, all auto-wire candidates within the container that match the expected type are provided to satisfy the dependency. You can auto-wire strongly typed map instances if the expected key type is string. An auto-wired map instance's values consist of all bin instances that match the expected type, and the map instance's keys contain the corresponding bin names. Limitations and disadvantages of auto-wiring. Auto-wiring works best when it is used consistently across a project. If auto-wiring is not used in general, it might be confusing to developers to use it to wire only one or two bin definitions. Consider the limitations and disadvantages of auto-wiring. 1. Explicit dependencies in property and constructor arg settings always override auto-wiring. You cannot auto-wire simple properties such as primitives, strings, and classes, and arrays of such simple properties. This limitation is by design. 2. Auto-wiring is less exact than explicit wiring. Although, as noted in the earlier table, Spring is careful to avoid guessing in case of ambiguity that might have unexpected results. The relationships between your Spring-managed objects are no longer documented explicitly. 3. Wiring information may not be available to tools that may generate documentation from a Spring container. 4. Multiple bin definitions within the container may match the type specified by the setter method or constructor argument to be auto-wired. For arrays, collections, or map instances, this is not necessarily a problem. However, for dependencies that expect a single value, this ambiguity is not arbitrarily resolved. If no unique bin definition is available, an exception is thrown. 1. Abandon auto-wiring in favor of explicit wiring. 2. Avoid auto-wiring for a bin definition by setting its auto-wire candidate attributes to false, as described in the next section. 3. Designate a single bin definition as the primary candidate by setting the primary attribute of its bin element to true. 4. Implement the more fine-grained control available with annotation-based configuration, as described in annotation-based container configuration. Excluding a bin from auto-wiring. On a per-bin basis, you can exclude a bin from auto-wiring. In Spring's XML format, set the auto-wire candidate attribute of the bin element to false. The container makes that specific bin definition unavailable to the auto-wiring infrastructure, including annotation-style configurations such as auto-wired. The auto-wire candidate attribute is designed to only affect type-based auto-wiring. It does not affect explicit references by name, which get resolved even if the specified bin is not marked as an auto-wire candidate. As a consequence, auto-wiring by name nevertheless injects a bin if the name matches. You can also limit auto-wire candidates based on pattern matching against bin names. The top-level beans element accepts one or more patterns within its default auto-wire candidates attribute. For example, to limit auto-wire candidate status to any bin whose name ends with repository, provide a value of repository. To provide multiple patterns, define them in a comma-separated list. An explicit value of true or false for a bin definition's auto-wire candidate attribute always takes precedence. For such beans, the pattern matching rules do not apply. These techniques are useful for beans that you never want to be injected into other beans by auto-wiring. It does not mean that an excluded bin cannot itself be configured by using auto-wiring. Rather, the bin itself is not a candidate for auto-wiring other beans. Method injection. In most application scenarios, Most beans in the container are singletons. When a singleton bin needs to collaborate with another singleton bin or a non-singleton bin needs to collaborate with another non-singleton bin, you typically handle the dependency by defining one bin as a property of the other. A problem arises when the bin lifecycles are different. Suppose singleton bin A needs to use non-singleton, prototype, bin B, perhaps on each method invocation on A. The container creates the singleton bin A only once, and thus only gets one opportunity to set the properties. The container cannot provide bin A with a new instance of bin B every time one is needed. A solution is to forego some inversion of control. You can make bin A aware of the container by implementing the application context-aware interface, and by making a getBinB call to the container ask for a typically new bin B instance every time bin A needs it. The following example shows this approach. Package fiona.apple//spring API imports. Import org.springframework.beans exception. Import org.springframework.context.application context. Import org.springframework.context.application context. Aware / a class that uses a stateful command style class to perform some processing. Public class command manager implements application context aware. Private application context application context. Public object process map command state / grab a new instance of the appropriate command. Command equals create command / set the state on the hopefully brand new command instance. Command.set state command state return command.execute. Protected command create command / notice the Spring API dependency. Return this .application context.getBin command.class. Public void set application context throws beans exception. This .application context equals application context. The proceeding is not desirable because the business code is aware of and coupled to the Spring framework. Method injection, a somewhat advanced feature of the Spring IOC container, lets you handle this use case cleanly. You can read more about the motivation for method injection in this blog entry. Lookup method injection. Lookup method injection is the ability of the container to override methods on container-managed beans and return the lookup result for another named bin in the container. The lookup typically involves a prototype bin, as in the scenario described in the preceding section. The Spring framework implements this method injection by using bytecode generation from the glib library to dynamically generate a subclass that overrides the method. 1. For this dynamic subclassing to work, the class that the Spring bin container subclasses cannot be final, and the method to be overridden cannot be final, either. 2. Unit testing a class that has an abstract method requires you to subclass the class yourself and to supply a stub implementation of the abstract method. 3. Concrete methods are also necessary for component scanning, which requires concrete classes to pick up. 4. A further key limitation is that lookup methods do not work with factory methods and in particular not with @bin methods in configuration classes, since, in that case, the container is not in charge of creating the instance and therefore cannot create a runtime-generated subclass on the fly. In the case of the command manager class in the previous code snippet, the Spring container dynamically overrides the implementation of the create command method. The command manager class does not have any Spring dependencies, as the reworked example shows. Package fiona.apple / no more Spring imports. Public abstract class command manager. Public object process object command state / grab a new instance of the appropriate command interface. Command equals create command / set the state on the hopefully brand new command instance. Command.set state command state return command.execute / OK. But where is the implementation of this method? Protected abstract command create command. In the client class that contains the method to be injected, the command manager in this case the method to be injected requires a signature of the following form. Public vertical bar protected, abstract, return type the method name no arguments. If the method is abstract, the dynamically generated subclass implements the method. Otherwise, the dynamically generated subclass overrides the concrete method defined in the original class. Consider the following example. Less than, a stateful bin deployed as a prototype, non-singleton, greater than. Less than, command processor uses stateful command helper, greater than. The bin identified as command manager calls its own create command method whenever it needs a new instance of the myCommand bin. You must be careful to deploy the myCommand bin as a prototype if that is actually what is needed. If it is a singleton, the same instance of the myCommand bin is returned each time. Alternatively, within the annotation-based component model, you can declare a lookup method through the @lookup annotation, as the following example shows. Public abstract class command manager. Public object process object command state. Command equals create command dot set state command state, return command dot execute. @lookup my command, protected abstract command create command. Or, more idiomatically, you can rely on the target bin getting resolved against the declared return type of the lookup method. Public abstract class command manager. Public object process object command state. Command equals create command dot set state command state, return command dot execute. @lookup protected abstract command create command. Note that you should typically declare such annotated lookup methods with a concrete stub implementation, in order for them to be compatible with Spring's component scanning rules where abstract classes get ignored by default. This limitation does not apply to explicitly registered or explicitly imported bin classes. Another way of accessing differently scoped target beans is an object factory/provider injection point. See scoped beans as dependencies. You may also find the service locator factory bin in the org.springframework.beans.factory.config package to be useful. Arbitrary method replacement. A less useful form of method injection than lookup method injection is the ability to replace arbitrary methods in a managed bin with another method implementation. You can safely skip the rest of this section until you actually need this functionality. With XML-based configuration metadata, you can use the replaced method element to replace an existing method implementation with another, for a deployed bin. Consider the following class, which has a method called computeValue that we want to override. A class that implements the org.springframework.beans.factory.support.method replacer interface provides the new method definition, as the following example shows. / meant to be used to override the existing computeValue string implementation in my value calculator. Public class replacement computeValue implements method replacer. Public object reimplement object O, method M, object, args, throws throwable, / get the input value, work with it, and return a computed result. String input equals, string, args0, return. The bin definition to deploy the original class and specify the method override would resemble the following example. bin.i.d. equals my value calculator class equals x.y.z. my value calculator greater than less than, arbitrary method replacement, greater than replaced method name equals compute value replacer equals replacement compute value greater than arg type string / arg type / replaced method / bin. bin.i.d. equals replacement compute value class equals a.b.c. replacement compute value, greater than. You can use one or more arg type elements within the replaced method element to indicate the method signature of the method being overridden. The signature for the arguments is necessary only if the method is overloaded and multiple variants exist within the class. For convenience, the type string for an argument may be a substring of the fully qualified type name. For example, the following all match java.lang.string. Because the number of arguments is often enough to distinguish between each possible choice, this shortcut can save a lot of typing by letting you type only the shortest string that matches an argument type. Bin scopes. When you create a bin definition, you create a recipe for creating actual instances of the class defined by that bin definition. The idea that a bin definition is a recipe is important, because it means that, as with a class, you can create many object instances from a single recipe. You can control not only the various dependencies and configuration values that are to be plugged into an object that is created from a particular bin definition, but also control the scope of the objects created from a particular bin definition. This approach is powerful and flexible, because you can choose the scope of the objects you create through configuration instead of having to bake in the scope of an object at the Java class level. Beans can be defined to be deployed in one of a number of scopes. The Spring framework supports 6 scopes, 4 of which are available only if you use a web-aware application context. You can also create a custom scope. The following table describes the supported scopes. Singleton. Default, scopes a single bin definition to a single object instance for each Spring IOC container. Prototype. Scopes a single bin definition to any number of object instances. Request. Scopes a single bin definition to the lifecycle of a single HTTP request. That is, each HTTP request has its own instance of a bin created off the back of a single bin definition. Only valid in the context of a web-aware Spring application. Context. Session. Scopes a single bin definition to the lifecycle of an HTTP session. Only valid in the context of a web-aware Spring application context. Application. Scopes a single bin definition to the lifecycle of a servlet context. Only valid in the context of a web-aware Spring application context. WebSocket. Scopes a single bin definition to the lifecycle of a WebSocket. Only valid in the context of a web-aware Spring application context. A thread scope is available but is not registered by default. For more information, see the documentation for simple thread scope. For instructions on how to register this or any other custom scope, see using a custom scope. The singleton scope. Only one shared instance of a singleton bin is managed, and all requests for beans with an ID or IDs that match that bin definition result in that one specific bin instance being returned by the Spring container. To put it another way, when you define a bin definition and it is scoped as a singleton, the Spring IOC container creates exactly one instance of the object defined by that bin definition. This single instance is stored in a cache of such singleton beans, and all subsequent requests and references for that named bin return the cached object. The following image shows how the singleton scope works. Spring's concept of a singleton bin differs from the singleton pattern as defined in the Gang of Four, Groovy, patterns book. The Groovy singleton hard-codes the scope of an object such that one and only one instance of a particular class is created per class loader. The scope of the Spring singleton is best described as being per container and per bin. This means that, if you define one bin for a particular class in a single Spring container, the Spring container creates one and only one instance of the class defined by that bin definition. The singleton scope is the default scope in Spring. To define a bin as a singleton in XML, you can define a bin as shown in the following example. Less than, the following is equivalent, though redundant, singleton scope is the default, greater than. The prototype scope, the non-singleton prototype scope of bin deployment results in the creation of a new bin instance every time a request for that specific bin is made. That is, the bin is injected into another bin or you request it through a getBin method call on the container. As a rule, you should use the prototype scope for all stateful beans and the singleton scope for stateless beans. The following diagram illustrates the Spring prototype scope. A data access object, DAO, is not typically configured as a prototype because a typical DAO does not hold any conversational state. It was easier for us to reuse the core of the singleton diagram. The following example defines a bin as a prototype in XML. In contrast to the other scopes, Spring does not manage the complete lifecycle of a prototype bin. The container instantiates, configures, and otherwise assembles a prototype object and hands it to the client, with no further record of that prototype instance. Thus, although initialization lifecycle callback methods are called on all objects regardless of scope, In the case of prototypes, configured destruction lifecycle callbacks are not called. The client code must clean up prototype scoped objects and release expensive resources that the prototype beans hold. To get the Spring container to release resources held by prototype scoped beans, try using a custom bin post processor which holds a reference to beans that need to be cleaned up. In some respects, the Spring container's role in regard to a prototype scoped bin is a replacement for the Java new operator. All lifecycle management past that point must be handled by the client. For details on the lifecycle of a bin in the Spring container, see Lifecycle Callbacks. Singleton beans with prototype bin dependencies. When you use singleton scoped beans with dependencies on prototype beans, be aware that dependencies are resolved at instantiation time. Thus, if you dependency inject a prototype scoped bin into a singleton scoped bin, a new prototype bin is instantiated and then dependency injected into the singleton bin. The prototype instance is the sole instance that is ever supplied to the singleton scoped bin. However, suppose you want the singleton scoped bin to acquire a new instance of the prototype scoped bin repeatedly at runtime. You cannot dependency inject a prototype scoped bin into your singleton bin, because that injection occurs only once, when the Spring container instantiates the singleton bin and resolves and injects its dependencies. If you need a new instance of a prototype bin at runtime more than once, see method injection. Request, session, application, and WebSocket scopes. The request, session, application, and WebSocket scopes are available only if you use a web-aware Spring application context implementation, such as XML Web Application Context. If you use these scopes with regular Spring IOC containers, such as the class path XML Application Context, an illegal state exception that complains about an unknown bin scope is thrown. Initial web configuration. To support the scoping of beans at the request, session, application, and WebSocket levels, web-scoped beans, some minor initial configuration is required before you define your beans. This initial setup is not required for the standard scopes, singleton and prototype. How you accomplish this initial setup depends on your particular servlet environment. If you access scoped beans within Spring Web MVC, in effect, within a request that is processed by the Spring Dispatcher servlet, no special setup is necessary. Dispatcher servlet already exposes all relevant state. If you use a servlet web container, with requests processed outside of Spring's Dispatcher servlet, for example, when using JSF, you need to register the org.springframework.web.context.request.requestContextListener servlet request listener. This can be done programmatically by using the Web Application Initializer interface. Alternatively, add the following declaration to your web application's web.xml file. Web app, listener class org.springframework.web.context.request.requestContextListener /listener class /listener /web app. Alternatively, if there are issues with your listener setup, consider using Spring's request context filter. The filter mapping depends on the surrounding web application configuration, so you have to change it as appropriate. The following listing shows the filter part of a web application. Web app, filter name request context filter name filter class org.springframework.web.filter.request context filter class filter mapping filter name request context filter name less than URL pattern URL pattern filter mapping web app. Dispatcher servlet, request context listener, and request context filter all do exactly the same thing, namely bind the HTTP request object to the thread that is servicing that request. This makes beans that are request and session scoped available further down the call chain. Request scope. Consider the following XML configuration for a bin definition. The Spring container creates a new instance of the login action bin by using the login action bin definition for each and every HTTP request. That is, the login action bin is scoped at the HTTP request level. You can change the internal state of the instance that is created as much as you want, because other instances created from the same login action bin definition do not see these changes in state. They are particular to an individual request. When the request completes processing, the bin that is scoped to the request is discarded. When using annotation-driven components or Java configuration, the @request scope annotation can be used to assign a component to the request scope. The following example shows how to do so. Session scope. Consider the following XML configuration for a bin definition. The Spring container creates a new instance of the user preferences bin by using the user preferences bin definition for the lifetime of a single HTTP session. In other words, the user preferences bin is effectively scoped at the HTTP session level. As with request-scoped beans, you can change the internal state of the instance that is created as much as you want, knowing that other HTTP session instances that are also using instances created from the same user preferences bin definition do not see these changes in state, because they are particular to an individual HTTP session. When the HTTP session is eventually discarded, the bin that is scoped for that particular HTTP session is also discarded. When using annotation-driven components or Java configuration, you can use the @session scope annotation to assign a component to the session scope. Application scope. Consider the following XML configuration for a bin definition. The Spring container creates a new instance of the app preferences bin by using the app preferences bin definition once for the entire web application. That is, the app preferences bin is scoped at the Servlet context level and stored as a regular Servlet context attribute. This is somewhat similar to a Spring singleton bin but differs in two important ways. It is a singleton per Servlet context, not per Spring application context, for which there may be several in any given web application, and it is actually exposed and therefore visible as a Servlet context attribute. When using annotation-driven components or Java configuration, you can use the @application scope annotation to assign a component to the application scope. The following example shows how to do so. WebSocket scope. WebSocket scope is associated with the lifecycle of a WebSocket session and applies to STOMP over WebSocket applications. See WebSocket scope for more details. Scoped beans as dependencies. The Spring IOC container manages not only the instantiation of your objects, beans, but also the wiring up of collaborators, or dependencies. If you want to inject, for example, an HTTP request scoped bin into another bin of a longer-lived scope, you may choose to inject an AOP proxy in place of the scoped bin. That is, you need to inject a proxy object that exposes the same public interface as the scoped object but that can also retrieve the real target object from the relevant scope, such as an HTTP request, and delegate method calls onto the real object. You may also use AOP scoped proxy between beans that are scoped as singleton, with the reference then going through an intermediate proxy that is serializable and therefore able to re-obtain the target singleton bin on deserialization. When declaring AOP scoped proxy against a bin of scope prototype, every method call on the shared proxy leads to the creation of a new target instance to which the call is then being forwarded. Also, scoped proxies are not the only way to access beans from shorter scopes in a lifecycle safe fashion. You may also declare your injection point, that is, the constructor or setter argument or auto-wired field, as object factory myTarget bin, allowing for a getObject call to retrieve the current instance on demand every time it is needed without holding on to the instance or storing it separately. As an extended variant, you may declare object provider myTarget bin, which delivers several additional access variants, including getIfAvailable and getIfUnique. The JSR 330 variant of this is called provider and is used with a provider myTarget bin declaration and a corresponding get call for every retrieval attempt. See here for more details on JSR 330 overall. The configuration in the following example is only one line, but it is important to understand the why as well as the how behind it. HTTP URL. HTTP URL. HTTP URL. HTTP URL, less than, an HTTP session scoped bin exposed as a proxy, greater than. Less than, instructs the container to proxy the surrounding bin, greater than. Less than, a singleton scoped bin injected with a proxy to the above bin, greater than. Less than, a reference to the proxied user preferences bin, greater than. To create such a proxy, you insert a child AOP scoped proxy element into a scoped bin definition. See choosing the type of proxy to create and XML schema-based configuration. Why do definitions of beans scoped at the request, session and custom scope levels require the AOP scoped proxy element in common scenarios? Consider the following singleton bin definition and contrast it with what you need to define for the aforementioned scopes. Note that the following user preferences bin definition as it stands is incomplete. In the preceding example, the singleton bin, user manager, is injected with a reference to the HTTP session scoped bin, user preferences. The salient point here is that the user manager bin is a singleton, it is instantiated exactly once per container, and its dependencies, in this case only one, the user preferences bin, are also injected only once. This means that the user manager bin operates only on the exact same user preferences object, that is, the one with which it was originally injected. This is not the behavior you want when injecting a shorter-lived scoped bin into a longer-lived scoped bin, for example, injecting an HTTP session scoped collaborating bin as a dependency into singleton bin. Rather, you need a single user manager object, and, for the lifetime of an HTTP session, you need a user preferences object that is specific to the HTTP session. Thus, the container creates an object that exposes the exact same public interface as the user preferences class, ideally an object that is a user preferences instance, which can fetch the real user preferences object from the scoping mechanism, HTTP request, session, and so forth. The container injects this proxy object into the user manager bin, which is unaware that this user preferences reference is a proxy. In this example, when a user manager instance invokes a method on the dependency injected user preferences object, it is actually invoking a method on the proxy. The proxy then fetches the real user preferences object from, in this case, the HTTP session and delegates the method invocation onto the retrieved real user preferences object. Thus, you need the following, correct and complete, configuration when injecting request and session scoped beans into collaborating objects, as the following example shows. Choosing the type of proxy to create. By default, when the Spring container creates a proxy for a bin that is marked up with the AOP scoped proxy element, a glib-based class proxy is created. Glib proxies intercept only public method calls. Do not call non-public methods on such a proxy. They are not delegated to the actual scoped target object. Alternatively, you can configure the Spring container to create standard JDK interface-based proxies for such scoped beans, by specifying false for the value of the proxy target class attribute of the AOP scoped proxy element. Using JDK interface-based proxies means that you do not need additional libraries in your application class path to effect such proxying. However, it also means that the class of the scoped bin must implement at least one interface and that all collaborators into which the scoped bin is injected must reference the bin through one of its interfaces. The following example shows a proxy based on an interface. Less than, default user preferences implements the user preferences interface, greater than. For more detailed information about choosing class-based or interface-based proxying, see proxying mechanisms. Custom scopes. The bin scoping mechanism is extensible. You can define your own scopes or even redefine existing scopes, although the latter is considered bad practice and you cannot override the built-in singleton and prototype scopes. Creating a custom scope. To integrate your custom scopes into the Spring container, you need to implement the org.springframework.beans.factory.config.scope interface, which is described in this section. For an idea of how to implement your own scopes, see the scope implementations that are supplied with the Spring framework itself and the scope Java doc, which explains the methods you need to implement in more detail. The scope interface has 4 methods to get objects from the scope, remove them from the scope, and let them be destroyed. The session scope implementation, for example, returns the session scoped bin. If it does not exist, the method returns a new instance of the bin, after having bound it to the session for future reference. The following method returns the object from the underlying scope. Object get string name, object factory less than greater than object factory. The session scope implementation, for example, removes the session scoped bin from the underlying session. The object should be returned, but you can return null if the object with the specified name is not found. The following method removes the object from the underlying scope. The following method registers a callback that the scope should invoke when it is destroyed or when the specified object in the scope is destroyed. See the Java doc or a Spring Scope implementation for more information on destruction callbacks. The following method obtains the conversation identifier for the underlying scope. This identifier is different for each scope. For a session-scoped implementation, this identifier can be the session identifier. Using a custom scope, after you write and test one or more custom scope implementations, you need to make the Spring container aware of your new scopes. The following method is the central method to register a new scope with the Spring container. This method is declared on the configurable bin factory interface, which is available through the bin factory property on most of the concrete application context implementations that ship with Spring. The first argument to the register scope method is the unique name associated with the scope. Examples of such names in the Spring container itself are singleton and prototype. The second argument to the register scope method is an actual instance of the custom scope implementation that you wish to register and use. Suppose that you write your custom scope implementation, and then register it as shown in the next example. The next example uses simple thread scope, which is included with Spring but is not registered by default. The instructions would be the same for your own custom scope implementations. Scope thread scope equals new simple thread scope, bin factory.register scope thread scope. You can then create bin definitions that adhere to the scoping rules of your custom scope, as follows. With a custom scope implementation, you are not limited to programmatic registration of the scope. You can also do the scope registration declaratively, by using the custom scope configurer class, as the following example shows. http URL http URL http URL http URL org.springframework.beans.factory.config.custom scope configurer org.springframework.context.support.simple thread scope. When you place AOP scoped proxy within a bin declaration for a factory bin implementation, it is the factory bin itself that is scoped, not the object returned from getObject. Customizing the nature of a bin. The Spring framework provides a number of interfaces you can use to customize the nature of a bin. This section groups them as follows. Lifecycle callbacks. To interact with the container's management of the bin lifecycle, you can implement the Spring initializing bin and disposable bin interfaces. The container calls after properties set for the former and destroy for the latter to let the bin perform certain actions upon initialization and destruction of your beans. The JSR 250 at post-construct and at pre-destroy annotations are generally considered best practice for receiving lifecycle callbacks in a modern Spring application. Using these annotations means that your beans are not coupled to Spring-specific interfaces. For details, see using at post-construct and at pre-destroy. If you do not want to use the JSR 250 annotations but you still want to remove coupling, consider init method and destroy method bin definition metadata. Internally, the Spring framework uses bin post-processor implementations to process any callback interfaces it can find and call the appropriate methods. If you need custom features or other lifecycle behavior Spring does not by default offer, you can implement a bin post-processor yourself. For more information, see container extension points. In addition to the initialization and destruction callbacks, Spring-managed objects may also implement the lifecycle interface so that those objects can participate in the startup and shutdown process, as driven by the container's own lifecycle. The lifecycle callback interfaces are described in this section. Initialization callbacks. The org.springframework.beans.factory.initializing bin interface lets a bin perform initialization work after the container has set all necessary properties on the bin. The initializing bin interface specifies a single method. We recommend that you do not use the initializing bin interface, because it unnecessarily couples the code to Spring. Alternatively, we suggest using the @PostConstruct annotation or specifying a POJO initialization method. In the case of XML-based configuration metadata, you can use the init method attribute to specify the name of the method that has a void no argument signature. With Java configuration, you can use the init method attribute of @bin. See receiving lifecycle callbacks. Consider the following example. Public class example, bin. Public void init, // do some initialization work. The preceding example has almost exactly the same effect as the following example, which consists of two listings. Public class another example bin implements initializing, bin. @override. Public void after properties set, // do some initialization work. However, the first of the two preceding examples does not couple the code to Spring. Be aware that @PostConstruct and initialization methods in general are executed within the container's singleton creation lock. The bin instance is only considered as fully initialized and ready to be published to others after returning from the @PostConstruct method. Such individual initialization methods are only meant for validating the configuration state and possibly preparing some data structures based on the given configuration, but no further activity with external bin access. Otherwise, there is a risk for an initialization deadlock. For a scenario where expensive post-initialization activity is to be triggered, for example asynchronous database preparation steps, your bin should either implement smart initializing singleton dot after singletons instantiated or rely on the context refresh event, implementing application listener context refreshed event or declaring its annotation equivalent at event listener context refreshed event class. Those variants come after all regular singleton initialization and therefore outside of any singleton creation lock. Alternatively, you may implement the Smart Lifecycle interface and integrate with the container's overall lifecycle management, including an auto-startup mechanism, a pre-destroy stop step, and potential stop/restart callbacks, see below. Destruction callbacks. Implementing the org.springframework.beans.factory.disposable bin interface lets a bin get a callback when the container that contains it is destroyed. The disposable bin interface specifies a single method. We recommend that you do not use the disposable bin callback interface because it unnecessarily couples the code to Spring. Alternatively, we suggest using the @predestroy annotation or specifying a generic method that is supported by bin definitions. With XML-based configuration metadata, you can use the destroy method attribute on the bin. With Java configuration, you can use the destroy method attribute of @bin. See receiving lifecycle callbacks. Consider the following definition. Public class example, bin. Public void cleanup, // do some destruction work, like releasing pooled connections. The preceding definition has almost exactly the same effect as the following definition. Public class another example bin implements disposable, bin. @override. Public void destroy, // do some destruction work, like releasing pooled connections. However, the first of the two preceding definitions does not couple the code to Spring. Note that Spring also supports inference of destroy methods, detecting a public close or shutdown method. This is the default behavior for @bin methods in Java configuration classes and automatically matches java.lang.autoclosable or java.io. Closable implementations, not coupling the destruction logic to Spring either. For destroy method inference with XML, you may assign the destroy method attribute of a bin element a special, inferred, value, which instructs Spring to automatically detect a public close or shutdown method on the bin class for a specific bin definition. You can also set this special, inferred, value on the default destroy method attribute of a beans element to apply this behavior to an entire set of bin definitions, see default initialization and destroy methods. For extended shutdown phases, you may implement the lifecycle interface and receive an early stop signal before the destroy methods of any singleton beans are called. You may also implement smart lifecycle for a time-bound stop step where the container will wait for all such stop processing to complete before moving on to destroy methods. Default initialization and destroy methods. When you write initialization and destroy method callbacks that do not use the Spring-specific initializing bin and disposable bin callback interfaces, you typically write methods with names such as init, initialize, dispose, and so on. Ideally, the names of such lifecycle callback methods are standardized across a project so that all developers use the same method names and ensure consistency. You can configure the Spring container to look for named initialization and destroy callback method names on every bin. This means that you, as an application developer, can write your application classes and use an initialization callback called init, without having to configure an init method equals init attribute with each bin definition. The Spring IOC container calls that method when the bin is created, and in accordance with the standard lifecycle callback contract described previously. This feature also enforces a consistent naming convention for initialization and destroy method callbacks. Suppose that your initialization callback methods are named init and your destroy callback methods are named destroy. Your class then resembles the class in the following example. Public class default blog service implements blog service. Private blog DAO. Public void set blog DAO. This .blog DAO equals blog DAO. / This is, unsurprisingly, the initialization callback method. Public void init, if, this .blog DAO equals null. Throw new illegal state exception the blog DAO property must be set. You could then use that class in a bin resembling the following. The presence of the default init method attribute on the top-level bin's element attribute causes the Spring IOC container to recognize a method called init on the bin class as the initialization method callback. When a bin is created and assembled, if the bin class has such a method, it is invoked at the appropriate time. You can configure destroy method callbacks similarly, in XML, that is, by using the default destroy method attribute on the top-level bin's element. Where existing bin classes already have callback methods that are named at variance with the convention, you can override the default by specifying, in XML, that is, the method name by using the init method and destroy method attributes of the bin itself. The Spring container guarantees that a configured initialization callback is called immediately after a bin is supplied with all dependencies. Thus, the initialization callback is called on the raw bin reference, which means that AOP interceptors and so forth are not yet applied to the bin. A target bin is fully created first and then an AOP proxy, for example, with its interceptor chain is applied. If the target bin and the proxy are defined separately, your code can even interact with the raw target bin, bypassing the proxy. Hence, it would be inconsistent to apply the interceptors to the init method, because doing so would couple the lifecycle of the target bin to its proxy or interceptors and leave strange semantics when your code interacts directly with the raw target bin. Combining lifecycle mechanisms. As of Spring 2.5, you have 3 options for controlling bin lifecycle behavior. 1. The initializing bin and disposable bin callback interfaces. 2. Custom init and destroy methods. 3. The at post construct and at pre-destroy annotations. 1. You can combine these mechanisms to control a given bin. If multiple lifecycle mechanisms are configured for a bin and each mechanism is configured with a different method name, then each configured method is run in the order listed after this note. However, if the same method name is configured, for example, init for an initialization method for more than one of these lifecycle mechanisms, that method is run once, as explained in the preceding section. Multiple lifecycle mechanisms configured for the same bin, with different initialization methods, are called as follows. 1. Methods annotated with at post construct. 2. After properties set as defined by the initializing bin callback interface. 3. A custom configured init method. 1. Methods annotated with at pre-destroy. 2. Destroy as defined by the disposable bin callback interface. 3. A custom configured destroy method. Startup and shutdown callbacks. The lifecycle interface defines the essential methods for any object that has its own lifecycle requirements, such as starting and stopping some background process. Public interface lifecycle. Void start. Void stop. Boolean is running. Any Spring managed object may implement the lifecycle interface. Then, when the application context itself receives start and stop signals, for example, for a stop/restart scenario at runtime, it cascades those calls to all lifecycle implementations defined within that context. It does this by delegating to a lifecycle processor, shown in the following listing. Public interface lifecycle processor extends lifecycle. Void on. Refresh. Void on. Close. Notice that the lifecycle processor is itself an extension of the lifecycle interface. It also adds two other methods for reacting to the context being refreshed and closed. Note that the regular org.springframework.context.lifecycle interface is a plain contract for explicit start and stop notifications and does not imply auto startup at context refresh time. For fine-grained control over auto startup and for graceful stopping of a specific bin, including startup and stop phases, consider implementing the extended org.springframework.context.smart lifecycle interface instead. Please note that stop notifications are not guaranteed to come before destruction. On regular shutdown, all lifecycle beans first receive a stop notification before the general destruction callbacks are being propagated. However, on hot refresh during a context's lifetime or on stopped refresh attempts, only destroy methods are called. The order of startup and shutdown invocations can be important. If a depends-on relationship exists between any two objects, the dependent side starts after its dependency, and it stops before its dependency. However, at times, the direct dependencies are unknown. You may only know that objects of a certain type should start prior to objects of another type. In those cases, the Smart Lifecycle interface defines another option, namely the getPhase method as defined on its super interface, phased. The following listing shows the definition of the phased interface. The following listing shows the definition of the Smart Lifecycle interface. Public interface Smart Lifecycle extends lifecycle, phased. Boolean is auto startup. Void stop runnable callback. When starting, the objects with the lowest phase start first. When stopping, the reverse order is followed. Therefore, an object that implements Smart Lifecycle and whose getPhase method returns integer.min_value would be among the first to start and the last to stop. At the other end of the spectrum, a phase value of integer.max_value would indicate that the object should be started last and stopped first, likely because it depends on other processes to be running. When considering the phase value, it is also important to know that the default phase for any normal lifecycle object that does not implement Smart Lifecycle is 0. Therefore, any negative phase value indicates that an object should start before those standard components, and stop after them. The reverse is true for any positive phase value. The stop method defined by Smart Lifecycle accepts a callback. Any implementation must invoke that callback's run method after that implementation's shutdown process is complete. That enables asynchronous shutdown where necessary, since the default implementation of the lifecycle processor interface, default lifecycle processor, waits up to its timeout value for the group of objects within each phase to invoke that callback. The default per phase timeout is 30 seconds. You can override the default lifecycle processor instance by defining a bin named lifecycle processor within the context. If you want only to modify the timeout, defining the following would suffice: org.springframework.context.support.default lifecycle processor. As mentioned earlier, the lifecycle processor interface defines callback methods for the refreshing and closing of the context as well. The latter drives the shutdown process as if stop had been called explicitly, but it happens when the context is closing. The refresh callback, on the other hand, enables another feature of Smart Lifecycle beans. When the context is refreshed, after all objects have been instantiated and initialized, that callback is invoked. At that point, the default lifecycle processor checks the Boolean value returned by each Smart Lifecycle object is auto startup method. If true, That object is started at that point rather than waiting for an explicit invocation of the contexts or its own start method. Unlike the context refresh, the context start does not happen automatically for a standard context implementation. The phase value and any depends on relationships determine the startup order as described earlier. Shutting down the Spring IOC container gracefully in non-web applications. This section applies only to non-web applications. Spring's web-based application context implementations already have code in place to gracefully shut down the Spring IOC container when the relevant web application is shut down. If you use Spring's IOC container in a non-web application environment, for example, in a rich client desktop environment, register a shutdown hook with the JVM. Doing so ensures a graceful shutdown and calls the relevant destroy methods on your singleton beans so that all resources are released. You must still configure and implement these destroy callbacks correctly. To register a shutdown hook, call the register shutdown hook method that is declared on the configurable application context interface, as the following example shows. Import org.springframework.context.configurable application context, import org.springframework.context.support.class, path, XML, application, context. Public final class boot. Public static void main final string, args, throws exception, configurable application context CTX equals new class path XML application context beans.xml. / add a shutdown hook for the above context. ctx.register, shutdown, hook. / app runs here. / main method exits, hook is called prior to the app shutting down. Application context aware and bin name aware. When an application context creates an object instance that implements the org.springframework.context.application context aware interface, the instance is provided with a reference to that application context. The following listing shows the definition of the application context aware interface. Public interface application, context, aware. Void set application context throws beans, exception. Thus, beans can programmatically manipulate the application context that created them, through the application context interface or by casting the reference to a known subclass of this interface, such as configurable application context, which exposes additional functionality. One use would be the programmatic retrieval of other beans. Sometimes this capability is useful. However, in general, you should avoid it, because it couples the code to Spring and does not follow the inversion of control style, where collaborators are provided to beans as properties. Other methods of the application context provide access to file resources, publishing application events, and accessing a message source. These additional features are described in additional capabilities of the application context. Auto-wiring is another alternative to obtain a reference to the application context. The traditional constructor and by type auto-wiring modes, as described in auto-wiring collaborators, can provide a dependency of type application context for a constructor argument or a setter method parameter, respectively. For more flexibility, including the ability to auto-wire fields and multiple parameter methods, use the annotation-based auto-wiring features. If you do, the application context is auto-wired into a field, constructor argument, or method parameter that expects the application context type if the field, constructor, or method in question carries the auto-wired annotation. For more information, see using auto-wired. When an application context creates a class that implements the org.springframework.beans.factory.binNameAware interface, the class is provided with a reference to the name defined in its associated object definition. The following listing shows the definition of the binNameAware interface. Public interface bin, name, aware. Void set bin name string name, throws beans, exception. The callback is invoked after population of normal bin properties but before an initialization callback such as initializing bin dot after properties set or a custom init method. Other aware interfaces, besides application context aware and bin name aware, discussed earlier, Spring offers a wide range of aware callback interfaces that let beans indicate to the container that they require a certain infrastructure dependency. As a general rule, the name indicates the dependency type. The following table summarizes the most important aware interfaces. Application, context, aware. Declaring application, context. Application, context, aware and bin name aware. Application, event, publisher, aware. Event publisher of the enclosing application, context. Additional capabilities of the application context. Bin, class, loader, aware. Class loader used to load the bin classes. Instantiating beans. Bin, factory, aware. Declaring bin, factory. The bin factory API. Bin, name, aware. Name of the declaring bin. Application, context, aware and bin name aware. Load, time, weaver, aware. Defined weaver for processing class definition at load time. Load time weaving with aspect in the Spring framework. Message, source, aware. Configured strategy for resolving messages, with support for parameterization and internationalization. Additional capabilities of the application context. Notification, publisher, aware. Spring JMX notification publisher. Notifications. Resource, loader, aware. Configured loader for low-level access to resources. Resources. Servlet, config, aware. Current servlet config the container runs in. Valid only in a web-aware Spring application. Context. Spring MVC. Servlet, context, aware. Current servlet context the container runs in. Valid only in a web-aware Spring application. Context. Spring MVC. Note again that using these interfaces ties your code to the Spring API and does not follow the inversion of control style. As a result, we recommend them for infrastructure beans that require programmatic access to the container.